Okay guys, welcome back. Now we are just gonna continue this tutorial based on the exciting session that we had before, and we were able to just use the stand model, which it was essentially in nature a polynomial of degree 2 or a quadratic function. And as you remember from the model that we had, and I'm just going to go back there, you saw that the model was normal, but essentially the parameter of the mean was quadratic in terms of, I should say, the woman's weight. Now, but there was a problem that we had. The problem that we had was essentially the fact that the model didn't converge. Because we saw that when we just do the, I should say, the trace plots, the problem that we encountered was essentially the fact that it showed that the four different chains that they were in parallel searching for the neighborhood inside the parameter space, they didn't just converge and stayed stably in a neighborhood that we said that the search has been just converged. Now, what was the problem with it? We basically know that there is always almost a guarantee that we just have a convergence in the long run in our stand model then. But how can we just improve our model? And how can we just make sure that we can just get to the convergence before we can just reliably have some estimates of the parameters that we are interested for? We have two methods. We are just going to deal with this in this tutorial. And the first one is going to be the fact that one of the things that we do essentially is the thing that we are just going to increase the number of the iterations. For example, if before we had, for example, 1,000 of iterations, we can just go ahead to just incrementally or drastically change the number of the iterations. That's the thing, which you can just as a trial error do that yourself. For example, just go for 2,000, 3,000, 4,000 and increase the level of the iterations until you just see that the model has converged properly. The other thing that we just want to do is essentially the fact that we are just going to talk about the step size. We are just going to reduce the step size of our model. But what is going to be the step size? We're just going to go ahead and check the model. But before that, I'm just going to talk about a little bit, I should say, on the whiteboard, what do we mean by the step size that we have? Okay, look at that. Imagine that all these, I should say, circles, that they are centered. Imagine that they do represent the log of, I should say, the log posterior. And all of them are log posterior. And now, imagine that for the algorithm that we have, which is going to be, I should say, hybrid Hamiltonian, I should say, or hybrid Monte Carlo, or Hamiltonian Monte Carlo, we just starts, I should say, starts the particle, for example, at this contour. We give this an initial momentum, and based, I should say, on, the steepness that the particle finds, based on this momentum, for example, it ends up, for example, at this point, which we call that point 1. However, in order to just make this path, to take this path, depending on how much is the momentum and the energy of the particle at initial position point 0, we say that, okay, we decided to have, let's say, for example, in a couple of steps. For example, imagine 1, 2, 3, 4, and 5. Within 5 steps, we are just going to get from point 0 to point 1 in the parameter space, which is going to be on these contours of the log posteriors. These 5 steps, essentially, they show that the leap frog. They essentially call the leapfrog, which we call that 1, 2, 3, 4, 5, 6. It's going to be the 6. And very naturally, you may think to yourself that, okay, you deduce that the distance and the length of each step, if I can call it, for example, as an epsilon, is going to represent, I should say, the step size in your model. The smaller is going to be the step size. The model is going to be a little bit, takes much longer, but at the same time, I should say, for example, the algorithm that you have, it's not going to get stuck anywhere, I should say, in the parameter space. And now, Then essentially we talked about what is going to be the leapfrog, which is the number of the steps. For example, from where the particle starts, from where you stop that particle, and you draw a sample from, I should say, from the posterior probability distribution. Then from there, for example, it can start, for example, to end up here, for example, point 2, and with the same step sizes, or probably from the same leapfrog that you had from before that. And now that we talked, we get a good intuition about what is the step size and what is a leapfrog. I'm just going to go back again to the R environment that we had, and I'm just going to remove the warm-up which I had. I let the system, I should say, finds the warm-up itself. And now, and however, so the thing which I forgot to mention here is that initially when you just run your R stand model, the algorithm itself, it decides what is going to be the first leapfrog that you have, and also what is going to be the step size. And these two parameters is going to be decided during the warm-up that you have in your, I should say, in your algorithm. Now, if I just go back there, and after that I just decided on the number of the iterations, which I drastically increase that, I'm just going to reduce the step size in my model. In order to do that, I'm just going to just put another argument inside the stand find and create a control, and I'm just going to say, okay, the control is going to be a list, and the item which I'm just going to redo, I should say, introducing the steps on the list is going to be the step size. And this step size, spelling is not correct, the list which I have is going to be the step size, and I said that the step size which I have, it's going to be something very small, which I can say, for example, it's going to be, for example, this value. You can always get a good estimate what is the initial step size in your algorithm by, I should say, by doing, I should say, the launch shiny stand. Just go to the check the step size, then just come with the step size which is going to be smaller from the one which you have. I'm just going to show that to you how we can just do that when we just run this algorithm. But however, before we just do that, we assume that, okay, we are going to deciding by a kind of a trial and error for the number of the iterations to be 7,000, and the step size, it's going to be reduced to a small size as the value which I have there. Even you can just go with the smaller one, but be careful if the step size it becomes too much small. I should say it takes the proposals that you're just going to get, I should say, in, I should say, your parameter space. It's going to be, I should say, it becomes too computationally intensive then. Now, I'm just going to execute the line, but before that, I have to just make sure that the package which I have for the R stand is properly, I should say, ticked, which means that the function is ready. I'm just going to execute that, and let's see if I can just have this model converge. I press the Control Enter, and you see that the chain started from here. It takes some time. You see that the chain we have, for example, from the 700 iterations. Now we are just having the 20% of the warm-up is completed, and now we are just moving ahead then. And now you can see that still we have the warm-up, because you remember the warm-up, the system designed it, it's going to be almost half of the number of the iterations. Because the number of the iterations that we had, it's 7,000, half of it is going to be 3,500. You see that the warm-up is done after 3,500, and after that we have the sampling then. It's going to continue like that until now we are at the chain 2. I'm just going to stop, I should say, the recording towards the end of the processing for chain number 4. I'm just going to get back and we proceed from where we just left it. Okay, now we are getting almost towards the end of the iterations on chain number 4. And now this is processed. We can ignore this warning message because it doesn't have to do anything with the model that we just created here. And now the model is created now, and we are ready to see if the model has converged after tuning the parameter of the step size on our parameter space. In order to check the convergence, I'm just going to do 3 different things here. The first one is going to be the quick check. I'm just going to check the trace plot of the model by excluding the warm-up samples that we had. I'm just going to execute that line by pressing Control Enter, and we see that, okay, I'm going to zoom these plots, it seems that the model that we have right now, it's comparably and significantly much different than the model that we had before, that the model didn't converge. You see that for the parameters of the alpha, beta, and gamma, and also the sigma, you see that the chains, the sampling of the chains for 7,000 iterations, and you see that the warm-up is excluded, they have almost transposed, I should say, superimposed on top of each other, which it means that the model has converged. Also, it's going to be very interesting if we have, I should say, I'm just going to go ahead for the library, for the shiny stand, which we did that also on the prior module, and we have this, I should say, installed to launch, I should say, the shiny stand, and I'm just going to use that as a quadratic model, as an object, which is going to be a stand fit object to execute that, and I expect a separate browser. It's going to get open, and I do get the separate browser with the for the shiny stand. The model is going to be the woman quadratic, and we have the diagnostics tab, and we see that, okay, also here we see that, for example, for the different parameters, for the alpha, beta, and gamma, for example, for gamma, we see that the gamma, I should say, the inference that we have for the gamma, it's centered around the best estimates, which is going to be the mean of the 7,000 times that we draw something from the posterior probability distribution. We read the estimates for, I should say, for the gamma, we brought it back, and we repeated that for 7,000 times. Then at the end, we just got the average of it there. And that's the thing which we do that in statistics. And now we see that also this is converged, and also you can just go on the tab, which is going to be on the far right of your model. You see that the step size information. You see that for the step size information, we can just get a rough idea that what is going to be the step size, I should say, for the model that we have. And later, you can also modulate, I should say, your step size compared to the ones which you have right now for the step sizes for each parameters then. Now also, there are many other things as the tree depth, and also, for example, also the energy information and the tree depth information. You can also use that as a parameter to tune and increase, for example, the tree depth that you have in your system as a control argument inside your stand function, as a hyperparameter to be tuned. Normally, we just start with the step size, and rarely we get to, I should say, the tree depth information in order to tune this for the convergence of our model. Normally, by increasing the number of the iterations and also reducing the step size of the model and algorithm, search algorithm, I should say, we can just get to the convergence in our model. However, the other thing that we can just do and make sure that the model converged properly, even without looking at the graph, we can just go ahead to just print the model that we had. We said that, okay, the model was called quadratic model, and let me just close that, the parenthesis, and execute the line. Okay, nothing, probably. Oh, the reason I do not see anything, always make sure that before, when you just leave the shiny stand, stop, I should say, the program. And when you stop the program, now you can execute any other lines. And that's the thing which I forgot to stop, that I should say, the running of the shiny stand, and that was the reason I couldn't just get the command on the R. You see that when you just use the print, you get this basic information, that the number of the iterations that you had, the warm-up, which is half of the number of the iterations, and also you see that, for example, for 4,000, for 4, I should say, times 3,500, you get, I should say, that 14,000 draws that we had from the posterior probability distribution. And now look at this one. We have the inverse, I should say, we have the estimates for, I should say, for all the parameters that we have, for the alpha, beta, gamma, and sigma, and the log posterior, which we are not going to work with that right now. But the thing which I just wanted to show that to you is going to be the R hat, which is essentially a kind of a statistics to measure the convergence. Then the R hat is somehow around 1, between 1.01 and 1. It means that the model has converged. And always you can see that the R hat can be always also used as a measure to check for the convergence of your chains at the neighborhood that they just stay there for, I should say, in your sampling problem then. And now, essentially, you saw that by changing some parameters, which was the number of the iterations, and also, importantly, create a control to reduce the step size in your algorithm, you can just make a model which reliably, you can just have it, I should say, converge and reliably make the best estimates of the model that you're looking for. And now, by saying that, I'm so excited to just work on a model, have it initially diverged, then now this is converged by tuning some parameters, and now the thing which you just want to do on the next tutorial, we are just going to, I should say, create another block into the stand functions that we had and see that the model how can just replicate its own, I should say, observation first. Then from there, we can just move on to the next stage of our tutorial then. Then I can't wait to see you on the next tutorial, and see you later then.